Okay, so next we're going to go over problem 3, and this is where we're going to determine if each situation is either going to be a discrete function or a continuous function. So when we're talking about discrete function, it's basically where you would have gaps in the graph of, the scenario. If you were to make a graph of whatever's going on, you would have like gaps, or you would have like jumps, discontinuities, we say. If it was continuous, it would basically never it would basically be a graph that would never stop. It will not never stop in terms of not never stop, not necessarily go to infinity, but it wouldn't be like broken up. Now let's look at the first one. So Susan has a savings plan where she places $5 a week in her piggy bank. So let's say if we were to graph this, we would have, like, let's say the weeks on the horizontal axis. So week 1, 2, 3, 4. And then the money saved on her on the vertical axis. So let's go by fives. 5, 10, 15, or the money in her piggy bank, I guess. Let's just put a dollar symbol. Now, since she's putting $5 per week, on week 1 you would have a point here. She would have $5. Week 2, she would have $10. Week 3, 15, and then week 4, 20. So you would have points like this looking like a scatter plot. Now, don't be tempted to like connect them with a straight line, because if you were to actually to be more specific on what was going on, assuming that there's no other money that she gets, she would have $5 up until week 2. So it would be like a horizontal line to here and then an open circle. Then she would jump to $10. And then it would be $10 all the way up to here, open circle here at 310. Then she jumps to $15. Then week 3, she has $15 up until week 4, where she jumps from 15 to 20. See, the graph is jumping. This is also what's called a step function if you keep on going on in your math life. But this is going to be a discrete graph or a discrete situation because it's not it's broken up. You have gaps in it. So A will be discrete. All right, problem B, we have the bouncy balls, and I guess maybe the amount of money they make per bounce. Or I guess maybe the amount of money they're charging for each bouncy ball. So it looks like we're going by twos. Oh no, by ones. 1, 2, 3, 4, 5, 6, 7. So we have a point here at 1, or 2, 1, 4, 2, 6, 3, and so forth. But you can see right away, since we're given a graph, that it's broken up into gaps. It's just a scatter plot. So then this would be a discrete situation. And in situation C, we have the temperature over time. Temperature in degrees Fahrenheit is decreasing as time, goes on. And even though we don't have the exact values or the values of the temperature, it's on a line that doesn't have any gaps or any jumps. It's on a continuum. It's a continuous line. So this would be an example of a continuous situation. All right, D, Marshall tracks the number of hits he gets each baseball game and is recording his number of hits for the season in a table. So again, this would be an example of a discrete situation because you would only get, 1 hit, 2 hits, 3 hits, 4 hits. You're gonna have gaps between those numbers. You're not gonna be able to have like 1.1 hits, 1.5 12 hits, 1.2 hits. There's always gonna be gaps. It's not gonna have whole numbers. Now you can make a graph and you would see that it would just be, set of points. But this would just be an example of a discrete situation. All right, the distance you traveled since the day began. Okay, so let's actually make a graph of this because this can be a little confusing sometimes. So let's go time of day. As soon as you wake up is 0. And maybe it doesn't matter. We'll say maybe it's 12th hour. And then the distance you traveled. Now, maybe at the start of the day, you're moving pretty slowly. So you're not covering much distance very fast. And then you go to school and then you have to drive and you go in a car, then you're at school and you sit in your class. And maybe in your class, you're probably gonna be in a class for an hour at a time. So even though you during classes it probably stays, you don't cover any distance, maybe because you're staying in the class and you walk to the next class. Walk to your next class, then you stay in your seat again for like another hour. And you keep on following this pattern. Now, even though there are periods of time where you're staying still, your distance is not increasing, but it doesn't matter because again, it's on a continuous line. You're not gonna have any gaps on this graph. So this would be a continuous situation. All right, and then for F, actually F somewhere here. Let's put it there. You have the number of gumballs and the cost. This again, you can graph it as a set of points. You could graph it as like 5, 1, 10, 2, kind of like this graph here. So you would have like a set of points, gaps, scatter plot, in other words. And so then you would have another discrete situation. Right. Now let's look at 4. Right, whether the relationship presented is a function or not. Okay, so you have the time a person has been riding the Ferris wheel versus their distance from the ground. Okay, so now, well, I think I skipped Ferris wheel. The time a person has been riding a Ferris wheel versus their distance from the ground. Now this is kind of interesting because as you know, Ferris wheel, you're gonna be at the top, then the bottom, and you're gonna go, you're gonna be repeating repeating how far you are from the ground. So let's say we have a graph over time and then distance. When you get on the Ferris wheel, maybe I should draw a little circle on it. I'll draw a Ferris. I'll try to draw a Ferris wheel. This is a Ferris wheel. Now, when you get on the Ferris wheel, you're going to get on at the bottom. So maybe that's like right on the ground, we'll say. Maybe you're a few feet above the ground, be technical. So maybe at time 0, you start here. But as soon as it starts rotating, let's say it's going this direction, clockwise, your distance increases. So it starts to do something like this. Or start to do something like this. Up until you get to the highest part on your Ferris wheel, you're at the max distance. And then you start going closer to the ground. Back until you get to the very bottom. So let's say you start over here. You're going to keep on going until you get to the very bottom again. And you're going to go back, around, over. And it's going to be like a wave, so to speak. So your distance will, change from, the very bottom, maybe like it's 3 feet. Let's just say it's 3 feet. Maybe to the top, it's like, let's just say 50 feet. But this would still count as a function because it's okay for this to happen. It's okay for you to have the same distance at different points of time. You just can't have different distances at one point in time. So this would be a function. The day in a calendar year versus the amount of sunlight on that day. Similar thing. Well, like on on a day on some let's just say today you have maybe 10 hours of sunlight. Tomorrow you have 10 and a half. The next day you have 10 hours of sunlight again. It's okay to have 10 hours of sunlight more than once. You just can't have like on one day, like today, you can't have 10 hours of sunlight and 12 hours of sunlight. It wouldn't make any sense. So this is okay to be a function. And again, your graph would look like this. Maybe we have day on the horizontal, and sunlight would be on the vertical. All right, C, the value of a Volkswagen Bug convertible from the time of first purchase in 1978 to now. Value. So maybe again, the time from purchase, let's say this is the time from purchase over, 1978 to now. So 0 up to whatever. I think it's like, maybe it's, over years, but from time 0 to now, the value, let's put like the money sign with cost. The value probably was, actually, maybe this could be an expensive. Maybe it's like a classic car. Let's just say the value is somewhere up here. Represents maybe, I don't know, $20,000. I have no idea. Let's say $20,000. And the value maybe decreased for a while, but then since we realized it was a classic, it increased, and maybe it's going up, up, up. So it went down in price and went back up in price, and it even had a price of $20,000 again. But again, that's okay. It's okay to have the same price at different points in time. You just can't have two prices at one point in time. So this would be a function as well. Person's name versus their phone number. So if you know someone's name, are you gonna be able to know their phone number? That's kind of what that is saying. And no, because you can have let's say many people with the name John, even with even with like the same first and last name. But just because you know their first and last name doesn't mean that you're gonna know their phone number. Like maybe John has a phone number 1, 2, 3, 4, 5, 6, 7, and the other one has a phone number 7, 6, 5, 4, 3, 2, 1. Each John Smith is going to have a different phone number most likely. So this is not going to be a function. We'll say no, not a function. The stadium in which a football player is playing versus the outcome, win or loss of the game. Okay, so that's saying that if you know what stadium they're playing, let's say they're playing in the Los Angeles Stadium. For it to be a function, that means you know that for sure what's going to happen. You know that either going to win or they're going to lose for sure. But like the stadium is not going to, guarantee them to win or guarantee them to lose. It could be either. They could win or they could lose. So this would not be a function because the stadium could have, have the team win sometimes, and the stadium maybe has the team what lose. It's not a function as well. A function would be if you know the input, that means you're going to know the output. As long as you have a formula, that is. Let's look at a couple more now where we're looking at, ordered pairs, or you think of them as like, points on a graph. So here we have the ordered pairs listed here. The domain would be the x values. So the domain would be the x values. So we write them as a list. That would be -7, 3, 8, -6, -2. Now make sure you write them again as a list with with these symbols here. These are called braces. They're like squiggly brackets. Now it actually doesn't even matter the order of the numbers on the inside. You can put them in any order. It's probably more convenient to put them in, numerical order, but technically it doesn't matter. The range, now you just put the y values. So 2, 5, 4, 5, 3. We don't need to repeat 5 again because we already listed it. And again, we use the braces again for that. Now, for this to be a function, you want to make sure that you don't have any of the x values being assigned to different y values. So the x values, -7, 3, 8, -6, -2. None of the x values even repeat. So this will be okay for a function. All right, B, the domain, x values again. And use the braces, put them in the set notation. So 9, 0, 4, 5, 2, 0, 3. And we don't need to repeat the 0 because we already have it. And the range are the y values. 2, 4, 0, 3, 7, -3, -1. And again, we use the braces for this. And then we see if it's a function. So here we have x is 0 going to 4. We have x is 0 going to -3. So we have the 0 being assigned to 4, and then it's also being assigned to -3. So this is not going to be a function because that's not what we want. That's what we don't want. We don't want that. We know x is 0. It has to always be assigned to the same number. All right, one more. C, the domain would be 1, 2, 3, 4, 5, 6, 7, 8. Again, we use our braces. 1, 2, 3, 4, 5, 6, 7, 8. And the range would be the y values 2, 3, 4, 5, 6, 7, 8, 9. Now let's see if this is a function. This is going to be okay because since none of the x values repeat, there won't even be any possibility of a violation. So this will be okay for a function. Okay, so I'm gonna pause there. Let me know if you have any questions on this portion of the practice test. And I'll try to clear it up in the comments. And let me know if if you know make if there's something that I could have done maybe to make a better graph or anything. Well, but all right, I'll hope to see you in the next video.